Welcome to our video on quantum computing versus classical computing. In this video, we'll be exploring the key differences between these two computing paradigms and how they are used in different applications. Classical computing, also known as digital computing, is what we've been using for decades to process and store data. It is based on classical bits, which can only be in two states, 0 or 1. Cut to a shot of a qubit. Host. Quantum computing, on the other hand, is based on quantum bits or qubits. Unlike classical bits, qubits can be in multiple states simultaneously, which allows them to perform certain computations faster than classical computers. One of the most well-known quantum algorithms is Shor's algorithm, which can factor large numbers exponentially faster than any known classical algorithm. This has significant implications for cryptography and cybersecurity. However, classical computing still has its advantages. For example, it is better suited for processing large amounts of data and for running certain types of algorithms, such as sorting and searching. Another challenge with quantum computing is that it is still in the early stages of development, and the technology is not yet as mature as classical computing. Many of the most promising applications of quantum computing are still largely theoretical, and it remains to be seen how practical they will be in the real world. Despite these challenges, there are still many exciting developments in quantum computing, and it has the potential to revolutionize industries ranging from finance to healthcare. Researchers are working hard to develop new quantum algorithms and hardware that can make quantum computing more practical and accessible. There are also many open-source quantum software tools and libraries that you can experiment with if you're interested in learning more about this exciting field. Quantum computing utilizes quantum bits or qubits, which can exist in multiple states simultaneously, allowing for complex computations to be executed much faster than classical computing. Classical computing, on the other hand, relies on binary digits or bits that can only exist in one of two states, 0 or 1. This limits the speed and complexity of computations that can be performed. Quantum computing has the potential to revolutionize fields such as cryptography, drug discovery, and financial modeling by solving problems that classical computers cannot efficiently handle. However, building and maintaining a quantum computer is a significant technological challenge due to the sensitivity of qubits to environmental factors and the need for specialized hardware and software. Additionally, while quantum computing may be faster than classical computing for certain tasks, it is not a one-size-fits-all solution and may not be faster or more efficient for every problem. Despite the challenges, many companies and researchers are investing in quantum computing and exploring its potential applications. Google, IBM, Microsoft, and other tech giants have already made progress in developing and testing quantum computers. As the field continues to advance, it will be important for individuals and organizations to understand the differences between quantum and classical computing and how they can best leverage these technologies to solve complex problems. One of the main differences between classical and quantum computing is the way they process information. Classical computers use binary digits, or bits, which can either be 0 or 1. Quantum computers, on the other hand, use quantum bits, or qubits, which can be in a state of 0, 1, or a superposition of both states. Another key difference is the way these systems handle errors. In classical computing, errors can occur due to hardware failures, software bugs, or other issues. To address these errors, classical computers rely on error correction codes and other techniques. In quantum computing, errors can occur due to a phenomenon known as decoherence, where qubits lose their quantum properties and behave more like classical bits. To combat decoherence, quantum computers use quantum error correction and other techniques. Quantum computing is still in its early stages, and there are many challenges that need to be addressed before it can become a mainstream technology. One of the biggest challenges is building reliable and scalable hardware that can support a large number of qubits. Another challenge is developing algorithms that can take advantage of quantum computing's unique properties and outperform classical algorithms. Despite these challenges, there are many potential applications for quantum computing, particularly in areas such as cryptography, optimization, and simulation. For example, Quantum computers could potentially break many of the encryption protocols that currently protect sensitive information, such as credit card numbers and government secrets. On the other hand, they could also be used to create new forms of encryption that are more secure than anything currently available. Finally, it's worth noting that quantum computing is not necessarily a replacement for classical computing, but rather a complementary technology. Many problems can be solved more efficiently using classical algorithms, while others may require quantum algorithms or a combination of both. As such, the future of computing may involve a hybrid approach that incorporates both classical and quantum systems. One of the most significant differences between quantum and classical computing is the way in which they process information. Classical computing relies on bits, which are represented by either a 0 or a 1. These bits form the foundation of all computer operations, from simple addition to complex algorithms. Quantum computing, on the other hand, uses quantum bits, or qubits. Qubits can exist in a state of both 0 and 1 simultaneously, allowing for exponentially more calculations to be performed at once. Quantum computers also have the potential to solve certain problems much faster than classical computers. For example, factoring large numbers is a notoriously difficult problem for classical computers, but quantum computers can solve it using Shor's algorithm. This has significant implications for cryptography and cybersecurity, as many encryption methods rely on the difficulty of factoring large numbers. However, quantum computers are still in the early stages of development and face significant challenges, including the need for extremely precise control of qubits and the effects of noise and interference on calculations. It remains to be seen whether quantum computing will be able to live up to its potential and revolutionize the field of computing as we know it. As researchers continue to explore the possibilities of quantum computing, it is clear that it has the potential to bring about significant advances in a wide range of fields, from drug discovery to climate modeling. By harnessing the power of quantum mechanics, we may be able to tackle problems that are currently beyond the capabilities of classical computers and open up entirely new avenues of exploration and discovery. Quantum computing is a new and exciting technology that promises to revolutionize the way we process information. But how does it differ from traditional classical computing? In this video, we'll explore the key differences between quantum and classical computing, and what this means for the future of computing. Script. Introduction. Hello, and welcome to this video on quantum computing versus classical computing. As our world becomes increasingly dependent on technology, it's important to understand the fundamental differences between these two computing paradigms. In this video, we'll discuss what quantum computing is, how it differs from classical computing, and what the future holds for this exciting technology. What is quantum computing? Quantum computing is a new type of computing that is based on the principles of quantum mechanics. Instead of using classical bits, which can be either 0 or 1, quantum computing uses quantum bits or qubits, which can be in multiple states at once. This allows quantum computers to perform certain types of calculations much faster than classical computers. How does quantum computing differ from classical computing? The main difference between quantum and classical computing is the way they process information. Classical computers process information in a binary fashion, using bits that can be either 0 or 1. Quantum computers, on the other hand, use qubits, which can be in multiple states at once. This allows quantum computers to perform calculations that would take classical computers a very long time to complete. Another key difference between quantum and classical computing is the way they store and manipulate data. Classical computers use electronic circuits to store and manipulate data, while quantum computers use quantum mechanical systems, such as atoms or superconducting circuits. What are the advantages of quantum computing? One of the main advantages of quantum computing is its ability to solve certain types of problems much faster than classical computers. For example, quantum computers are particularly good at solving optimization problems, which involve finding the best solution to a complex problem. They are also well suited for certain types of cryptography, such as breaking encryption codes. What are the limitations of quantum computing? Despite its many advantages, quantum computing also has some limitations. One of the biggest challenges is that qubits are very fragile and susceptible to noise and errors. This means that quantum computers require sophisticated error correction and fault tolerance techniques to ensure the accuracy of their calculations. Another challenge is that quantum computers are currently very expensive and difficult to build. They require specialized equipment, such as cryogenic cooling systems, and are often housed in specialized facilities that are designed to minimize external noise and interference. What is the future of quantum computing? Despite these challenges, many experts believe that quantum computing has the potential to revolutionize the way we process information. In the future, we may see quantum computers used to solve some of the world's most complex problems, from climate modeling to drug discovery. Conclusion. In conclusion, quantum computing represents a major breakthrough in computing technology. While it is still in its early stages, the potential applications of quantum computing are vast and far-reaching. Whether it's for solving complex optimization problems or breaking encryption codes, quantum computing has the potential to transform the way we live, work, and interact with the world around us. YouTube-style ending. That's all for today's video on quantum computing versus classical computing. We hope you found this information useful and informative. If you have any questions or comments, please leave them in the comments section below. And don't forget to subscribe to our channel for more videos on the latest developments in technology and science. Thanks for watching.